My drone has been trying to kill itself. Motors have literally caught on fire, and I've watched the drone rip itself apart mid-air. Burned through so many frames that I've started treating them like disposables. And the whole time, I kept thinking, just one more issue. But eventually, it clicked. The structure wasn't stiff enough, and at high RPM, even a tiny flex can turn into a vibration monster that escalates into total failure. So I reprinted the parts in PPA-CF, and for the first time, I saw a difference that actually matters. Not perfect, not magically fixed, but real progress. Today, I'm breaking down what PPA-CF is, why stiffness matters so much in drone frames, what changed on my build, and why more people aren't using this material for drone frames and structural parts. When people hear vibration, they think of a shaky GoPro clip. But on a drone, vibration is a chain reaction. You've got high RPM motors creating energy at certain frequencies. If the frame or motor mounts flex even a tiny amount, the drone stops being a rigid platform and starts being a spring. And springs don't just shake. Springs store energy and then release it back into the system, which is where you get resonant throttle zones, parts loosening over time, screws backing out, fractures forming in the exact same spot, and in my case, full-on failures that escalate way beyond annoying vibration. This is the important part. Strength and stiffness are not the same thing. Strength is, does it break? And stiffness is, does it flex? And for drones, stiffness is the one that makes everything else easier, because stiffness helps your geometry stay locked. Motor alignment stays consistent, your stack isn't getting hammered with noise, fasteners aren't constantly being worked loose, and the whole structure stops amplifying vibration. If your drone flexes, the whole thing basically becomes a resonance amplifier. So what is PPA-CF? PPA is polyphthalamide, a high-temp nylon family polymer. You will also see brands call it PAHT, or high-temp nylon. CF is chopped carbon fiber mixed into the plastic. The carbon fiber doesn't just make the material cool, it changes how the material behaves. It increases stiffness, it improves dimensional stability, and it gives prints that matte composite feel. The first time you hold a PPA-CF print, it usually feels less like plastic and more like a functional part. Now, I'm not claiming PPA is a magic spell, but here's what changed for me immediately. The first big thing was that parts stopped acting like springs. On my drone frame, the motor area and structural pieces felt like they held their shape under load way better. And when you're fighting violent vibration, that's the difference between chasing random failures and finally getting a stable platform you can actually diagnose. And that stiffness doesn't just help durability, it helps everything. Your vibration energy doesn't get amplified as easily, parts don't fatigue as fast, and you stop getting that it's fine until it suddenly isn't behavior. Drone parts are basically worst case conditions for 3D printed plastics. Constant vibration, high frequency stress, heat near the motors, and repeated impacts and hard landings. So you want a material that's stiff, heat tolerant, dimensionally stable, and still tough enough to survive real use. PPA-CF is one of those filaments that checks all those boxes in the real world, not just on paper. This is the part in the video that I want to talk about, because after seeing what it's doing for my build, I'm confused why it's not more common. Here are the reasons why I think people aren't using it. Moisture management scares people off. PPA-CF is nylon family. It absorbs moisture. If you don't dry it, you get poor surface, weak layer bonding, worse mechanical performance. So people try it once, hate it, and never go back. 2, I don't have a printer for that. A lot of builders can print PLA, PETG all day, but PPA-CF usually wants higher nozzle temps, better thermal control, and ideally an enclosed case. And 3, carbon fiber sheet frames already dominate. Traditional carbon fiber plates / arms are already incredible. So most drone builders think, why would I print structure? And honestly, they're not wrong for standard builds. But printing wins in these categories: custom geometry, flat iteration, unusual mounts, integrated features, prototypes, or specific parts that you want to tune or redesign quickly. People chase strength and not stiffness. A lot of the drone community focuses on will it snap, but stiffness is what prevents the vibration spiral in the first place. 5, fear of Z weakness. 3D prints are weaker between layers. If you don't design for that, orientations, parameters, geometry, it's easy to make a bad structural part, even out of great material. But if you're printing motor mounts, arm interfaces, stack mounts, camera mounts, antenna, GPS mounts, vibration critical brackets, PPA-CF starts to make a lot of sense. If you want PPA-CF to be the material that everyone raves about, then there are a few non-negotiables. Dry it like you mean it. This is the difference between monster material and why did I waste my money? Hardened nozzle. Carbon fiber is abrasive. Don't run brass. Good layer bonding. For drone parts, layer bonding is light. You need temps and settings that prioritize adhesion. Design like it's structural. If the part's job is stiffness, add parameters, add ribs, widen interfaces, reinforce motor mount regions, and avoid skinny plastic Y features. Here's the mindset I'm using now. Perimeters over infill for structural stiffness, ribs and gussets for where vibration concentrates, clamp style mounts instead of thin plates when possible, orient prints so the load isn't trying to peel layers apart, and when in doubt, make the vibration critical zone thicker. Because for drones, I'd rather add a few extra grams than add a new failure mode. So that's where I'm at. PPA-CF is the first filament that's meaningfully helped my drone stop acting like a self-destructing vibration machine, because it's not just strong, it's stiff. Now I want to hear from you. Why do you think people aren't printing drone frames in PPA-CF? Is it cost, moisture, printer limits, or is it just because carbon fiber plates are already the answer? If you liked today's video, make sure to like, subscribe, and share. Thanks for watching. Bye.